Have you ever wondered where the granite for your countertop comes from? Well, it comes from the Canadian Shield and it can be up to 300 million years old. Today, we're going to talk about the changing Earth. So, the theory is that the Earth has a long history of development and change that lasts billions of years. Recently, scientists tend to agree that the Earth is about 4.5 billion years old. And we're going to discuss events that shaped and continue to shape our world. And we're going to ask the question, how do we know how old the Earth is? So if we think that the Earth's entire deep time history is happening in just 24 hours, those 400 generations would have taken only 0.2 seconds of that day, which is virtually an instant in geological time. And these are the 400 human generations that have existed. Major changes in the Earth's structure but take millions of years to occur, but all of human history has occurred only in the last 100,000. So we cannot have observed the changes that have occurred. We can't have observed the Grand Canyon forming or the Rocky Mountains forming or the Pacific Ocean getting becoming the shape that it is today. Also, it's not possible to dig a hole to China, even though so much of what we know about the Earth's structure is just theory. We're going to look at three major topics over the course of this unit. One, how the physical structure of the Earth has changed. Two, how the conditions needed to support life, such as climate, have changed, and the impact of these two changes on the type of life found on Earth. So when we look at the changing Earth's structure, we can make direct observations about how the Earth's surface has changed over shorter periods of time. So we can see things like erosion or volcanic eruptions, deposition of sediment. We can see how tides are changing and the changing levels of oceans and the changes in glaciers. We also have evidence that indicates that the Earth's crust has moved and continues to move. And we can see this in the formation of mountains and canyons, as well as the short-term effect of earthquakes. So this is section C1.1. The Precambrian Shield was a red belt of granite rock, and it's now called the Slave Granite. And this formed part of the Canadian Shield. It was formed in the Precambrian era, which was the first major section of geological time, and it lasted from 4.5 billion years ago to up to 590 million years ago, so roughly 4 billion years. So when we're looking at the American continent, North American continent, it makes up more than half of Ontario's landmass, including most of Ontario and Quebec. So we can kind of see it here in that kind of beigeish yellow color going over Nunavut, Northwest Territories, northern Saskatchewan, northern Manitoba, and most of Ontario and Quebec. And I think there's a tiny little corner covering Alberta as well. But that's the Canadian Shield. Generally, in Alberta, you're going to have to dig several thousand meters below the surface to reach granite rock. But when a rock layer that's normally underground and exposed, like the Slave Granite could be, it's called an outcrop. So this would be when it's normally underground, but through some geological fashion, it is now exposed and we can visualize it. When we look at granite, we can see large mineral crystals of a variety of shapes and sizes peppered throughout. This is why people like it for their countertops, because it has a nice visual appearance. And some of these minerals can only be formed under high temperatures between 900 and 1,000 degrees Celsius and very high pressures. So this occurs deep down under the Earth's surface. When we're considering the structure of the Earth, we only see the outer layer, but the Earth can be separated into layers that are arranged according to their densities. The densest components form the densest layers and they sink to the center, and then the least dense components float to the surface of the Earth. So if we're comparing the Earth to an egg, the yolk is the core, the center of the Earth, and there is a solid inner core and a liquid outer core. And the core is the densest layer of the Earth, and it's made up of nickel and iron. And then the liquid core spins compared to the rest of the planet. And that spinning of the liquid core induces the Earth's magnetic field. So that inner core spinning or that liquid core spinning is what's going to induce our electric field. And we can see it there. It's about 29,000 kilometers thick, and it is in the kind of darker gray. And then below that, we see the inner core at 5,100 kilometers, and it's solid. And none of these are exactly to scale. So the layer of the Earth between the crust and the core is called the mantle. And comparing it to an egg, this would be considered the egg white. It makes up about 80% of the Earth's volume, and we have it here in oranges, different shades of orange, which is why this isn't to scale, because it would be about 80% of the volume. The extreme heat and pressure within the mantle causes rocks to behave as plastic. So the temperature there and the pressure causes rocks to become pliable, which is why we can have which is why there's an increase in the increase in temperature causes that to happen. In the layers of the mantle, we have the asthenosphere, and this is the uppermost layer of the mantle. It's the least rigid and most plastic part of the mantle. We can see this when magma from the asthenosphere rises up in the form of volcanoes. Okay, so the asthenosphere is the top of the 3 layers of the mantle. The rest of the mantle beneath the asthenosphere is more rigid. This layer is known as the mesosphere. Finally, there is the lithosphere, which is like the shell of the egg. The lithosphere includes the solid oceanic crust and the continental crust that floats on the asthenosphere. Okay. And the oceanic crust could be roughly 4 to 7 kilometers thick, where the lithosphere is about 75 kilometers thick. So we can't dig to China, because not only would we have to go through magma, but we would also have to go through a solid iron or nickel core, which isn't possible. So it's in the mantle, there are convection currents. So as hot magma, which is melted rock, rises and expands, it cools when it reaches the crust, and then it falls. And so this creates a current in the mantle. And this current causes our crustal plates to move. And crustal plates are also known as tectonic plates. And these are large pieces of crust, either continental or ocean, that float on the mantle and slowly move atop the asthenosphere. So you could again visualize the Earth. So for a hard-boiled egg, that the shell has been cracked. And then all those separate layers of crust can move on that semi-liquid magma. So when we're looking at tectonic plates, the Earth is covered with them. The ocean floor ones are continually moving. They're a lot thinner and closer to the magma, and they spread from the center, sink at the edges, and are being regenerated. So sometimes they'll spread apart and new magma will come from above. Sometimes one will go underneath the other one, and then it will turn into magma. And some of them will spread apart, and then when they spread apart, they can maybe go underneath the continent at the edges. Because the continental crusts might be thicker and heavier. So the convection currents beneath the plates move the crust in different directions. So some places the crust is moving apart from the next crustal piece, and in some places the crust is moving towards the next crustal piece. And the source of all these convection currents is heat from radioactivity deep within the Earth's core. So to look at some evidence of plate tectonics, one of the things we can look at is paleomagnetism, so the study of the magnetic properties in trenches. So when we look at deep ocean trenches, what are the different magnetic properties there? We can look at mountains, which are where there's folded layers of soil and rock. So you can see in this mountain picture that the layers of rock almost go vertically instead of horizontally, as they would be deposited over time. Volcanoes and hot springs occur. This gives us a glimpse into the heat that's deep within the Earth's crusts. And we have mid-ocean ridges and ocean trenches. So again, because those ocean crusts are thinner, we can see more clearly that separation of a crust, or we can see where 2 crust plates come together. So we have 3 types of plate boundaries. We have divergent boundaries, and this is where new crust is generated as 2 plates pull away from each other. And this is going to be the site of ocean ridges and valleys. So as those two plates pull away from each other, magma is able to come up from the asthenosphere and fill in new crust where there's gap. Convergent ground boundaries is where one crust is destroyed as one plate dives under another. And this is often the site of mountain ranges, valleys, and volcanoes. So as one crust goes underneath the other, it might push that one up and it might form a mountain. Those two edges might touch and go down and form a valley. And this is also where volcanoes are likely to happen because that magma, as one crust is going underneath the next, is much more closer to the surface. And we also have transform boundaries. So transform boundaries are where plates slide horizontally past each other, so like this. And this is often the site of earthquakes, as those plates don't always move seamlessly. Maybe they might catch and then all of a sudden move very quickly, causing an earthquake. So, plate boundary zones are just general broad belts where the boundaries are not really well defined and the effects of the plate interaction are unclear. So, we can't identify this down into a simple, this happens over a 3-kilometer area. So, we have plate boundary zones where all this action is occurring. So, when we look at the slave granite that makes up the Canadian Shield, geologists think that slave granite rock was formed at a collision site of two continental crystal plates about 2 billion years ago. So about halfway through the Earth's history. Since these plates had roughly equal densities, one plate could not slide under the other plate. So those plates were welded together, pushing up huge rock wrinkles to form mountain ranges. At the site of this weld, granite was formed due to the immense amount of heat and pressure, and then it was pushed up. But over the last 2 billion years, those mountain ranges will have eroded. And then the slave granite is it's not mountains, but it's still there. And this is some of the oldest rock in Alberta. So, like I said, that slave granite we just see in the very northeastern tip of Alberta, even though it covers most of Ontario and Quebec. Alberta only has a very little bit. So, I hope you enjoyed our lesson today on the Earth's history. Take it easy.